Welcome back to another lecture from organic chemistry. In last lecture, I mentioned this, that when the compound goes through fragmentation, it will try to create or generate the most stable carbocation and also radical as well. And we said the tertiary carbocation is more stable than the secondary and then the primary. And of course, the primary is way more stable than the methyl group. And I have to say this one, we have the same trend also for the radicals. So the tertiary radical, it will be the most stable radical. Now, if your compound happen to have a lone pair, and first thing that is going to happen, the lone pair, it will lose an electron, and it will give you this species. So you have really high chance to see, to see the molecular ion if there is a lone pair there. And because we are losing just one electron, the molecular ion, or the peak that you will get technically, not only is a molecular ion, it will have the molar mass of your compound. Now, if there is a ring, because that ring, it can stabilize it can stable the carbocation or the radical, and you have a better chance of ionization, and so the intensity, it will go up if there's a ring there, or there is a double bond. And if there is no double bond or a ring, then you're going to be dealing with just a sp3 hybridization, and for example, for cyclohexane, and the most stable carbocation that you can get, it will be secondary, which is less stable than, for example, than carbocation and is a neighbor, to a pi system. Okay. I have three molecules, hexane, 2-methyl, and 2-methyl pentane, and 3-methyl pentane. And these three molecules are constitutional isomers. Formula for them, it will be C6H14, and the molar mass, it will be 86.14. So molar mass, it will be 86.14. Okay, and this peak, the last peak that you see here, that's going to be technically the molecular ion peak. Okay, now we need to connect these structures to three spectrum that we have, and in order to speed it, I already labeled them, and so as you see, the first one, or A, the dominant peak, it will be 57, so I'm going to put a star on it, and for B, again, still is 57, but we do have like a good intensity for the molecular ion there, and for C, the dominant peak, it will be 43. Okay, so 57 kind of like got disappeared, and now 43 is the dominant peak. Okay, let's see how we can tackle this equation. So I know the molar mass is 86.18, and like in the case of hexane, I have either primary or a secondary carbon. Okay, so two primary and the rest are secondary. Now, when I can put the scissor anywhere, so I can cut the molecule from here, there, or there. But if I cut the molecule from somewhere here, I get two particles that they are the same. They have molar mass of 43. Okay, or if I cut it from here, that's going to give me ethyl, and this piece, it will have molar mass of 57. Okay, and because I have either primary or secondary, there is not much difference between them. I'm going to say I'm going to have a chance to see this, the molecular ion. So the one that has higher intensity for the molecular ion, I'm going to say there is a high chance that compound is going to be linear, because there is not much difference between the carbocations that we are creating, either secondary or primary. Okay, so the one that it has like higher intensity for an molecular ion, it will be the hexane. Next thing is, what will happen if we cut the molecule from here? If we cut it from there, then we will get M minus 15. But if we cut it from here, we will get M minus 29. Okay, M minus 15, it has a molar mass of 71, and M minus 29, it has a molar mass of 57. Okay, now let's go back. Okay, between A and B, okay, A and B, as you see, the base peak is 57. Okay, so clearly there is a huge preference for 57, and in both cases. And next thing is A. In case of A, the molecular ion is really weak, the intensity for it, while this one is much better. Okay, so I'm going to say this one, it can be hexane. So I will sign it as hexane. Now, if I remove CH3 from it, it will give me 71, which is M minus 15. And how about this peak? It will be M minus 29, or minus technically ethyl group. And how about the 43? Why do I get 43 there? 43, as I said, if you cut the molecule from here, you get two identical peaks. So let me clear it a bit. So let's say we decided to chop the molecule from here, and in that case, we get two propyls, and each one is going to have M over Z equal to M over Z equal to 43. And because I get two of them, I'm going to see high intensity for that actual signal. Okay. So 43 M over Z, we're going to see that one as well. So not only 57. Okay. So the first is like B, I will assign it to hexane. Now let's see how we can differentiate A from Z, A from C. The main difference between them is here. 57 is gone, or really, really low. And now the base peak is not 57 anymore. The base peak is 43. So let's name this one the base peak. Okay. And so I have one structure that is favoring 57. The second is favoring 43. And let's see which one is favoring 43. If you cut this molecule from here, you get 2 points. You get two species. One is this, or you might get this one. And in both cases, M over Z is 43. Okay, so whether you put it on the secondary carbon or the primary carbon, when I say you put, I'm talking about the positive charge, whether you put it on secondary or a primary carbon, M over Z, it will be 43. Well, if you cut this molecule from somewhere here, okay, or from there, okay, so either that one, okay, see here, if you decide to cut the molecule from here, you get this species, which has mass of M over Z of 57. And if you cut it from there, you get the same thing. So I have two positions that they are identical, and both of them, they will give me this. That's going to favor M over Z equal to 57. So the one that has 57 as a base peak, I'm gonna say it will be the 3-methyl pentane. So the 3-methyl pentane, it will be A. Okay. And the one that it has a base peak of 43, it will be the 2-methyl pentane. So this is going to be, okay, or let's say this one here, the 2-methyl pentane, it will be C. Okay. Again, the way I differentiate them, I look to 57. I said I have a higher chance to get 57 by breaking a molecule from here or there. They are identical. These two are identical. And so in both cases, I get 57. And well, if I cut the molecule from here, that's going to give me 43. And as you see, 43 is the dominant peak. So 2-methyl pentane, it will be, it will show up as like the C spectrum belongs to technically 2-methyl pentane. We have 4 molecules, 2-methyl pentane with molar mass for it is 114.23 gram per mole. Next one, 2 and 4 dimethyl pentane. This one is 100.21 gram over mole. Next, heptane will be 100.21 gram over mole. And last one is hexane is 86.18. Okay, now the top molecule, it has 8 carbon. So this one, it will be C8H18. This one is it has 7 carbon, so it will be C7H16. And heptane, it will be C7H16. The last one is hexane, it will be C6H14. Okay, so only 2 of the molecules have the same formula, or technically same molar masses. Okay, heptane versus 2-methyl 2 and 4 dimethyl pentane. Okay, now I'm going to look to the molecular ion. This is the molecular ion. The molecular ion peak, it says it's 100. So clearly in this case, A cannot be the answer, and D as well. Okay, because they have molecular ion of 86 and 114. So those two are gone. Now, how do we differentiate the, B from C? Let's draw the molecules. Okay, this is, okay, heptane, 1, 2, 3, 4, 5, 6, 7, versus second molecule, we said is pentane, 1, 2, 3, 4, 5, and it says 2 and 4. Okay, 2 and 4. Here you go, 2 and 4. Now, this molecule, if you start cutting this molecule, either one, let's say this one is the heptane. If you start chopping the molecule, you can chop it from here, there, or there. Okay. You have the option to technically create CH3, this one, CH3, CH2, CH3, CH2, and then we get CH2. Okay. And of course, we can get those 3 times, and then CH2. Okay, that's 5. And last one, you can get that, well, that molecule. Okay, so the first one, and okay, and then for this one, I can say that's going to be M minus, it will be M minus 15, and here M minus like 29 because we lost an ethyl. And so if you cut it from here, you get M minus 15. Okay, and let's say you decided to put the positive charge there, that's going to be the last species, or like you can actually put the positive charge on methyl. In that case, you get CH3. Okay. How about the second one? Second one, I can cut the molecule from here, so it's going to give me CH3. Okay. Next one, if I cut it from here, also CH3. Okay, so I can get CH3 plus, okay, what else? If I cut the molecule from here, I get this species. Okay, it has M over Z of 43. Okay, there we had 15. This one 29. That one is 43. Okay, so still I see it. And what else? How about the molar mass of this species? This one we have 4 carbons, and so molar mass, or M over Z of this one, it will be 57. Okay, and do we have the 57? Yes, we see the 57 here. Okay, so not much difference. The only difference between them, okay, the top one, it can create this signal. Okay, the 29. There is a way for us to create the 29, or technically lose an ethyl. Okay, so instead of 29, let's say that we can technically create this species M minus 29. We can lose an ethyl, but for the second molecule, there is no way for you to take an ethyl group from it. So I'm going to look for this peak. Which compound it has M minus 29? Which compound is capable of losing 29 from the molar mass? Okay, let's look back here. I see a peak is 71. I go 100 minus 71, that's 29. Okay, so if this is M, this one, it will be M minus 29. Okay, how about this one? That's going to be M minus 43. Okay, that means we lost an ethyl propyl group. And as you see, both of them are capable of losing propyl group, but only the top molecule, only heptane, is capable of losing ethyl. So I'm going to say this molecule must be heptane. And why? Because only heptane can create this peak for you. M minus 29. Only heptane can lose ethyl group. So I'm going to technically cut the molecule from here, and put the positive charge there. And so this one, it will be M minus ethyl, or minus 29. Okay, and M, you have 100 minus 29. You should see a peak around 71. And I do see that peak. Well, I don't see it for the second molecule. So I'm going to say this species, this spectrum must belong to heptane.